Alright, Max, how do we go about finding the inverse of this equation for a male shoe? What does inverse mean? Switch x and y. Step 1, switch x and y. So y'all, I asked Max that. He hadn't said, no one had said it yet. Who in here remembers when you read inverse, you switch x and y? Thumbs up. That means you're on track. If you're not knowing that, you need to write it down, make yourself a note, study inverse. You don't know what that word means, you need to go back and study it. All right, next move. After you switch x and y, what do? Matthew? Get y alone. That part looks a little bit different in each equation. So I'm gonna get fancy here, and I'm gonna say m with a little -1 to show inverse of x is x plus 22 divided by 3. Yeah, go ahead. Because this y has nothing else next to it. There's no other number next to y, so stop when y is alone. Go ahead. Yeah. Really good, really good. If we were going to graph, I would really prefer this. So what you did was right for graphing. I just knew that the problem wasn't asking for graphs, so I stopped there, but this is great. Yeah. Well, letter B, I believe they're implying that the name Lucy is female. No, it says each. That means do both.
I'm redoing the part meeting.
Okay, so now we'll do the female formula. F of x is 3x minus 21. No, I'm just gonna do it real quick. So maybe you want to write it 1/3 x plus 7. Did you guys give that a chance to go ahead and make that a 7? So that's a good opportunity to split the fraction when you can reduce the number like that. So for this one, go ahead and label it that this is s -1 x.
You had to do the male part too?
Yeah, it said find the inverse of each. That means do both. So that's letter A. Letter B says Lucy wears a 7.5. How long is her foot? are we going to solve this one? Which one though? Should I plug it into the one that I've been given or the new one that I wrote? Yeah. Where do we plug 7.5 in the one given or the new one? Well, let's look. Let's look at the words. This is kind of the point. This is some reading comprehension here. In this given equation, x is the length of the foot and y would be the shoe size. So for Lucy, we're looking at the female one. So if I were to focus on this, x is the length of foot and y is shoe size. All right, now when we rewrote this inverse switches that, okay? So this time, x is shoe size and y is the length of the foot. And this is why inverse functions are actually important if you want your equation written differently because you have the other information. So in this equation, I would have the length of the foot and I would put it in here and it would tell me what shoe size I need. But in this equation, it's if I have a shoe size and I need to find the length of the foot. Here, they told us Lucy's shoe size and they want to know the length of the foot. So we're going to pick the inverse because the inverse switched what was solved for. So plug 7.5 into here. And this will tell you Lucy's shoe size. Are your feet 7.5 inches? Oh, do you wear, the question is, do you wear a 7.5 shoe size? Because in that case, you're Lucy. Do you know how long your foot is? Okay. All right. What do most people know? Do most people know the length of the foot or their shoe size? Most people know their shoe size. I wouldn't think so. No, that would be dividing because the 3 would be on the bottom. That's dividing. Alright, so everybody, you guys can go home and measure your feet. Well, for the girls anyway, if you wear a 7.5 shoe size, your foot is 9.5 inches. So if you wear something more than that, your foot is longer. If you wear something less than that, then your foot is shorter. So can you guys think of a situation where, Emily, you know your shoe size. Could you think of a situation where you might want the length of your foot? If you're getting custom shoes. Yeah. Like, does anybody dance in here? Like, how to dance shoes work? Well, with point, yeah. Is that what you were gonna say? Oh no, I did taco shows. Okay, so I don't know. The measurement. Yeah. So if I had to like quick think, well, I don't know how long my foot is, but I know where I said 8. That equation would tell me how long my foot is. All right. Number 41. 41. Ready? Ready? Paige, can you read 41?
Yeah. The formula for the area of a circle is A equals pi r squared.
Find the inverse of the function. So this is more SAT material here. This one. Just put your phones away.
Can I
Matt.
Can I round decimals?
Yeah. Okay, keep it in terms of pi.
Because 36 divided by pi.
Oh.
I'll just keep it. And then just use my calculator.
Alright, so our inverse. In a literal formula like this, finding the inverse is not so obvious. Like, how do I switch x and y when there's no x and y? So find the inverse in this means pretty much isolate the other variable. Well, switch r. Well, we're actually not going to switch them. We're just going to solve for r. So I'm going to divide pi on both sides. Square root. Matthew. Do you guys think we need a plus or a minus? We square rooted both sides. Should we use a plus or minus? Trick question. What?
You would need it. Because you square root both sides.
It's not that pi is positive. Radius can't be negative. Actually, radius, area, and pi can't be negative. So in this geometric formula, there's no plus or minus. You all are losing points every time you're starting a conversation like this. Okay, I'm going to start documenting it. Shouldn't be necessary.
You said area, radius, and what was the other value that can't be negative?
Pi. Well, you can have a negative pi, but like in and of itself, it's not negative, right? So this is positive, so this whole thing will always be positive.
Okay, so it's area, radius, and pi. Always be positive?
Yeah. Because pi is 3.4, it's not like plus or minus 3.14.
Yeah.
Okay, so that's letter A. Use the inverse to find the radius of a circle with an area of 36. So if you're given area, this equation is more helpful. If you're given radius, the starting equation was more helpful. So we'll use our answer from letter A, plug in 36 for the area. Yeah, let's go ahead and write this as a decimal. Round to the thousandth. So 3.39 would be the radius. Centimeters. Yeah. Yeah. Square root of 36 divided by pi. Tori?
Oh, you square rooted first.
100. That would be the 100th. Thousandth would be There you go. Yeah, that's all I did was square root that fraction. Oh, so your decimal will be a little bit off if you divide it and then round it.
Yeah, because I did 338513751. Yeah, that's the exact answer that I have. Oh, I am good.
Alright, get out your homework. Get out your homework. Who knows what time this class ends? So you guys know what? I'm actually gonna check your homework tomorrow and we're gonna go right to notes right now.
With me.
I'm checking for it tomorrow. You need to do it. Yeah, so good, so good, so good. I don't feel good. Alright, this is quiet. I have a lot to tell you in the next few minutes, so moving into chapter 6-3 is square root functions. So square root functions, you guys do not have to copy all of this. This is not for copying down in a busy way. We want to be able to graph a square root function and identify domain and range. So what I have here is an example of a bad table, an example of a better table. See how this green one says better? So before you just start writing anything down, consider why one table is better than the other one. So the equation that you're working towards knowing how to graph is this. Correct. So you're learning a brand new graph, and the equation has a square root bar in it. So you want numbers that square root easily. So the table that makes sense for this function is unlike any other table you've made before. It's 0, 1, 4, and 9. Because those numbers are the first 4 numbers that can square root. Square root of 1 is 1, and the square root of 4 is 2, and the square root of 9 is 3. So this is like a mental math table for this function. Whereas if you rely on the -2 through 2 that sometimes you do with graphing, you end up with imaginary numbers because you can't square root a -2. And then you end up with decimals because you can't square root 2 either. It's irrational. So for this function, you don't want to just make any old table. You want to really think about numbers that square root well. So this is the table you should copy into your notes. Okay? If you want to copy the bad example, you go right ahead. Or take a picture, whatever you want. But this is the best table for the square root function. The parent square root function, which is the most basic. Can anybody tell me what might be the best next x value in the green table? You have another one, Julie. What's the next one? 36. Yes, 36 works. Good. We're at 9 minutes.
Can we do 16 first? Before the 36?
Yes, can I help you? So I'm going to draw a picture of what this looks like. It's pretty unique. Yeah, better. We're pretty much going to ignore this. It's just an example of why it doesn't work. 0, 0, 1, 1, 4, 2, and 9, 3. So this graph kind of looks like a wave. What's unique about it is it doesn't have an arrow on both sides. So it's kind of like a ray in geometry, but it has a curve to it. Yeah, let's hear domain and range. You got it. Well, looking at the picture, you look and see where the green line goes. And this green line doesn't go into the negatives. And it can't, but you can't square root a negative. It would be imaginary. It wouldn't show up here. Yes. Yeah. Oh, I could have put 2 here, but I would have a decimal. And I kind of have to use a calculator because I don't really know the square root of 2. I could have put 5, but I don't know the square root of 5, so it's just not ideal. This is the most ideal table. Great question. Okay, generally tables don't define domain and range of functions. The graphs do. Alright, so transformations with this function are the same as the transformations in absolute value functions and quadratic functions.
What is this? Note still? What you doing? You always have stuff.
No, this is square root function. Alright, you guys keep your conversations down. Keep your conversations down. So, A indicates a stretch, compression, or reflection like it always has. H underneath the radical bar shows a horizontal shift, shift left or right. And K at the end is a vertical shift, a shift up or down. This is super helpful. The end point is H comma K. So this one ends at 0, 0. But as soon as we start adding numbers in, this dot moves around. So the end point is the number in the H spot and the K spot. Yeah. So what we did a few months ago looked like this. This is a quadratic. This is that inverse. Okay. So a quadratic looks like this. If you turn the quadratic function diagonally and reflect it, you get this shape. You only have half of it because of the definition of function. So it's the exact opposite. So for this one, y equals the square root of x minus 5 minus 3. You're going to start with this picture, and then you're just going to move it around. So I'd like to highlight that the end point would be 5, negative 3. So instead of starting right at 0, 0, this graph is going to be shifted right 5 and down 3.
Oh, and it's a thing that if it's negative or it's
So now the domain is x greater than or equal to 5, and the range is y greater than or equal to negative 3. We shifted the graph right 5 and down 3. Yeah, because this and this make this endpoint. It's similar to how this was a vertex. We put that and then we just drew the U-shape around it. This was a vertex in our quadratics. In that, it's an endpoint. I'm just copying this shape down here. So this is over 1 up 1, and this is over 4 up 2, over 9 up 3. So I challenge you for your assignment to try 2 of these transformations. It's page 81, just number 4 and just number 6. You should be able to start with the green graph here and just move it. And tomorrow I'll give you a whole list of problems for you to practice the bigger graph. Yeah, work with.